And hello OpenFormers, welcome back. Testing. Okay, mic work. The mic is working. Okay, so in the last video, we were talking about some possible causes of the bug that we are doing. So we found that the write interval wasn't the problem. It's not about the sampling time as well. Alright, so well, the other thing we want to check out is the FV schemes and FV solution. Okay, so we found this problem. Now we have this thing called you have this thing called the max iteration is 0, and we are not sure whether that maybe this is one of the reasons why this file is giving us non-temperature calculation kind of a bug. Alright, so yeah, we see this as one of the problems, because when we look at the hot room case, VI system and FV solution, we see there's no max iteration entry over here. Now that may be one of the reasons why the temperature is not calculating. Second of all, of course, you see there's a scheme for the E over here. Alright, so here you have UHK epsilon omega and R. Here you have UHE and K epsilon omega and R, where E is for like some internal energy. Alright, one of those thermodynamic properties. So let's take a look at the bug log. So maybe we need to enter an entry for calculating E. Okay, part C. Perhaps there's something different with the FV schemes. Okay, what am I talking about? So clear. Let's go to time varying cavity foam system, and let's go to FV schemes. Alright, now there are entries for almost everything, and then there's this thing called bounded Gauss linear. Alright, let's see what the buoyant pimple foam time varying boundary condition will say. System FV schemes. Oh, it should be a VI system FV schemes. Now here we find something pretty different. Alright, so the DTT scheme is an Euler scheme, gradient scheme is a Gauss linear. However, when you talk about divergence of phi u, phi k, phi h, and phi small k, we see something called bounded Gauss linear. Now what is this? Alright, let's go. Okay, this is irrelevant. So very important for us to learn is this solution and algorithm control. Alright, as well as numerical schemes. This is something we got to learn to deal with the solvers in OpenFOAM. These are our input files for the solver. Okay, so what are we talking about here? Here we are talking about divergence schemes. So we go to divergence schemes. So this is a subdictionary containing divergence terms. So for example, divergence of phi and u here, divergence of phi and u refers to the flux. Phi equals to rho times u. So this is what this is talking about. Okay, so the entries required are Gauss and whatever interpolation scheme it is. So Gauss linear is kind of the default way. Okay, so and then we see this thing called Gauss linear upwind, which is over here. Alright, then we see Gauss linear again. Then we see this thing called bounded Gauss limited linear. So where do we see the bounded? Okay, we don't really see a bounded Gauss linear here. But if you search online, this is called the limited linear divergence scheme. You can see this thing called limited linear, and then it's bounded into 0.2. That's the entry. So limited linear schemes will be something like that, where they kind of fix the gradient, okay, over here, so that it's artificially set to 0. So that's not something we want. Usually you go for a linear divergence scheme where you have something like this. The gradient is straight throughout. Okay. So again, you have a linear upwind, something like this. You do not want, you basically you do not want it to set itself up like that. Perhaps that's the reason why the fields are not calculating correctly. So let's see whether changing all this to either Gauss upwind or Gauss linear will solve our problem. Okay, so if we look at the upwind scheme, upwind divergence scheme. So this is what the scheme looks like. Alright, so we can change all to some sort of a Gauss linear kind of a scheme. Alright, which is what we want. Okay, so this is Gauss linear. We'll go for Gauss linear for all of them. Okay. Alright. So I'm gonna do linear for all of them. So Gauss linear. Better make sure the syntax is right. So I'm going to fast forward this. So now basically I changed every of the schemes to a Gauss linear scheme. Okay, this one I need to correct. Insert and press an R and WQ. Alright, so we can move on to the FV schemes. FV solution. System FV solution, just for comparison. Alright, VI FV solution. Alright, we'll change just to add the E entry in here. Okay, and also in the final one. Okay, so we'll leave the max iteration as 0 here, and let's see whether it calculates out correctly what we want. Okay, so I'm going to clear, and we can do a update of the bug log. Okay, so trial solution, change, add the entry for E in FV solution, add the entry for Gauss linear instead of bounded Gauss limited linear for FV schemes. So that's part of the debug. Alright, so I'm going to do all clean, all run, and so I'm going to fast forward. Okay, so we have some results now. So I'm going to touch time vary.form, and I'm going to bring ParaView up. Let's see whether this helps us with the with our bug. Okay, so we have a solid temperature profile coming out. So this is temperature at T equals 1, temperature at T equals 2, T equals 6. Again, nothing's changing for some reason. So that doesn't seem to solve the bug. So let's take a look at the temperature inside. VI, okay, VI12.T, and then we'll have this file. Again, it's the same bug here. Okay, so I'm gonna probably have to stop this simulation, and let's take a look at the bug log. Okay, so trial solution results doesn't help calculate T. Okay, so write and quit, but let's see whether there's a U. Yeah, our velocity file is writing very nicely. So yeah, VI0, CD0, CD time varying cavity foam, VRT. Well, perhaps yeah, next thing we want to do is to see whether the problem lies with the uniform fixed value boundary condition. Okay, or okay, let's do the bug log properly first. Okay, VI bug log time varying temperature. Let's put number 4. Maybe the time varying BC is to blame, so that we can try and investigate later. So, oops. Not the issue. And then here, not the issue. Okay. Okay. So maybe we take a look at this max iteration entry being 0. Right. So we are almost done calculating. Okay, clear. So it's reaching about 84 seconds now, so it's pretty fast. Should be clearing things up pretty quickly. 86, 87, 88. So give it about 1 minute, you should be able to finish. So I'll fast forward that. Yes, so we're almost done. Clear. And we'll do our all clean because that obviously didn't work. And let's try now getting the max iteration out. Let's get the max iteration out. Maybe this is the problem because this entry is absent over here and it's over here. And let's see what max iteration does. I mean, just for the sake of learning. Okay, max iterate. So again, it says here, sparse matrix solvers are iterative. They are based on reducing the equation residual, meaning to say when you iterate, there's a solution at iteration I and a solution at iteration I plus 1. So I think the difference between them is sort of a residual. So is to measure the error in the solution. So the smaller it is, the more accurate the solution. So when of course you do it, you converge. Alright, so before solving an equation for a particular field, the initial residual is evaluated based on current values of the field. After each solver iteration, the residual is evaluated. The solver stops if either of the following conditions are reached. The residual falls below the solver tolerance. The ratio of the initial value residuals falls below the relative solver tolerance, RLTOL, or number of iterations exceeds a maximum number of iterations, max iteration. So having a max iteration of 0, it will just basically stop everything. Okay. All right. So let's look entry by entry. All right. So we have a ρGH solver with a relative tolerance here. Okay. And then we have UHEK, omega R, all this. This is about the same as here. All right. Then we have the rho star. 0, 0. Sure. So if it should work. PRGH final. Also a 0. UHEK blah 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 final. We have a relative tolerance of 0, and then we get a entry from U. So entry from U, it's over here. You will copy and paste all of this down into here. And yeah, we have a max iteration, which should not be 0. I'll just delete that off. Hopefully that solves the thing. So let's see. Okay, let's remove the swap file. Okay, VI bug log, trial solution, delete max iter 0 entry. Okay, let's see what happens. I'll run. And vi log.buoyantpaperfoam. Let's see what's happening. Alright, so it's solving for iterations. Alright, so fast forward to see whether this is the problem. So anyway, we observe the log.boil-pimple-foam file. We see that the delta T is 0.0011. It's stabilizing over there. It'll probably take a while for it to work past the time equals 1. So okay, it looks good. At least the simulation seems to be moving forward. Okay, it might take a while. So I'm going to fast forward this video and we'll see the results of the first second. Yeah. And we're almost at the first time step. Okay, time equals 1 is very close by. Just want to take note of something. Okay, so when we set it, we begin to notice that our execution time takes way longer. This is probably a good thing because now the iterations are running properly to convergence. So for example, we have the H here, which has 1 iteration. Then there's a final initial residual of this much, the initial error. And the final error is this much, which is pretty small, which is below the tolerance. Same for this. PRGH, we have a 104 iterations. Alright, so time step, continuity error. Okay, pretty small. So this is all iterating to convergence. So this is a good thing, a good sign. It means since we are calculating more fields, we are calculating some turbulence fields and some temperature fields, we expect the simulation to take longer. And at least for comparing the last few runs of the time varying cavity foam to now, the simulations are running longer. So that means that there are more fields being calculated, and that probably means that the temperature field is also being calculated. Okay, so we have our first data after so long. So let's go and see what's inside. 1 and T. Okay, great. Look at this. We have a varying temperature field. Okay, 299, 300. It's a nice varying temperature field here. You see it's 481 over here. So let's touch time vary.foam, and let's open ParaView. So it looks like we are having the correct temperature calculations. Okay, so at least there are temperature fields showing up. Okay, time vary.foam. Oh, it's a long 40 minutes of debugging. So yes, take a look at this. Now our temperature fields are calculating. We can see some convection currents being set up, and the temperature is about 600 degrees, which was the same as different from before, which was like fixed at 500 and something. But we take a look at this. It's beautiful. There's a convection current. If there's a convection current, that means this thing is probably working correctly. So it's going up, it's swirling around, which is probably what we want, the effect that we want to see. Okay, so probably this simulation is going to take a few hours just to finish, judging from like the first second taking about 10 minutes. So 10 times 100 seconds will give you about 1,000 minutes, which is easily like a few hours. All right. No, 10 minutes, right? Oh, let's see how long this. All right. So okay. So 1 second, it took about, let's see, 800 seconds. So let's give a rough calculation. 800 divided by 60, that's about 13 minutes for 1.2 seconds, or 10 minutes per second. So we want 100 seconds times 10 minutes divided by 60. It will take about 16 hours to finish the simulation. So that's way too long for this video. However, let's take a look again at our temperature fields. 1 and T. Let's go all the way to the bottom. See? Now the value is a uniform at 589.659. This is very different from what we started with. So let's go to VI0. Oops, sorry. VI0 and T. Okay, so this is what we started with, the CSV file. And now the the temperature CSV file, it's oscillating correctly. It at least that's what it looks like, right? 1 and T. Okay, so it's uniform at 589.659. So at least the CSV file is not the problem. So let's go and update our bug log, and then we'll call it a day for this video. Alright, so VI bug log, time vary temp. So we delete it. It seems to work. The combination of changing FV solution and FV schemes has allowed the simulation to work. Okay, so the time varying BC is not to blame. Okay, so this is just a bug log so that we can push it up on GitHub. Alright, so I'm just going to clear. I'm going to git add, git commit, and debugging complete with 1 second of data for time varying cavity foam. Alright, so anyway, that's all we have for the debugging. Hopefully that's helpful in helping you understand what's going on behind the solvers.
And in debugging, you usually learn a lot more than, copy and paste, and then the whole thing just works. So thankfully, the simulation is properly debugged now, and then we can sort of see the effects of the results of the time varying foam, the time varying temperature condition much later on. Okay, so I'm going to push. Alright, so I'll put the links below. These numerical simulation links and all the limited divergence scheme in the video below. So thanks for watching. Thanks for your patience in my debugging. So now we see that the time varying boundary condition kind of starts to work after we've done some debugging. So I'll see you guys next time. Bye bye.